Hello students, let's start solving the theory questions from the chapter Metals and Non-Metals which came in the board exam 2025. Okay, let us see this question. The first part says that displacement reactions also play a key role in extracting metals in the middle of the reactivity series. Justify this statement with two examples. Now we have already seen even when we are doing MCQs also, zinc and lead are also are there in the middle of the reactivity series. Now their oxides are reduced using carbon into the respective metal. Now, it's not always compulsory we use carbon or carbon monoxide. Now, there are certain elements which also belong to the middle of the reactivity series. Those are your iron and manganese. And manganese iron exists in the form of Fe2O3 and manganese exists in the form of MnO2. Now these two oxides, instead of using carbon, okay, we have the option of using a highly reactive element in the reactivity series. Okay, we can use a highly reactive element in the reactivity series and do the reduction of these oxides into the respective metals. For that, we have chosen a very good option, that is aluminium. Aluminium belongs to the highly reactive metals in the reactivity series. Now, instead of using carbon or carbon monoxide as the reducing agent for these oxides, we are going with aluminium as the reducing agent, which is a highly reactive metal. So, one point you have to remember here: oxides of the metals in the middle of the reactivity series can be reduced using the highly reactive metals above the reactivity series. Now, you people know the reactions way the highly reactive metal displaces the low reactive metal from its oxide or halide. We call those reactions as displacement reactions. What do we call those reactions as? Displacement reactions. Now you can see here, as aluminum is more reactive than manganese, aluminum can displace manganese from its oxide form. So what do you get here? You get Al2O3 plus manganese. You get Al2O3 plus manganese. As I already mentioned you, all metal oxides exist in the form of solids. Aluminium is a solid because it is a metal, and aluminium oxide is a metal oxide, so it is solid. Manganese, though it is a metal, here you get manganese in liquid form, that is your molten form. What is the reason behind it? We will see. Okay, now let's start to balance this reaction quickly. I have two aluminium. So, okay, here I have one, but here I have two oxygens. Here I have three oxygens. What is the only way I balance it? I'll put two here and I'll put three here. Okay, now I have three manganese atoms here. So let me put three manganese here. Here I have four aluminium atoms. Okay, let me put four aluminium here. Clear? I think this reaction is balanced now with respect to all the atoms which we see. Yes, it is balanced. Now, what do I do? Okay, now very, very important point you need to remember. As I already told you, it is a displacement reaction. It is a displacement reaction. And the very important thing you need to remember, it is also, okay, in this reaction, it is also a very highly exothermic reaction. Because we have a very highly reactive metal involved here, this is a highly exothermic reaction. Now you get enormous amount of heat coming outside. This heat is responsible for the melting of manganese. Usually manganese, we expect it to come in a solid form because it is a metal, or we expect it to be there in solid form because it is a metal. But because of the high amount of heat released in this reaction, the manganese melts into the molten form and we call it as molten manganese. Okay, in the same way, we can do this even for iron here. Fe2O3, Fe2O3 plus Al. Aluminium can even reduce your iron oxide. Okay, here if you see, iron is in +3 oxidation state, so you should call it as, you can call it as ferric oxide, or you can just say iron 3 oxide. Okay, it undergoes reduction, and what do I get here? I get Al2O3 plus Fe. Now, if you try to balance it, I have two Fe2F iron atoms here, so here I will put two Fe. I have two aluminium atoms here, so here I will put two aluminium. I think the reaction is balanced now. Now let us write the physical states. Metal oxides are solids. Here aluminium is a solid. Metal oxides are solids, because as I told you, these reactions are highly exothermic reactions. Okay, now you get lot of enormous amount of heat over here. That is the reason whatever iron I have obtained, it is in the molten form. It is in the molten form. So these are the two elements. manganese and iron, which are in the middle of the reactivity series, and we use highly reactive elements to displace them, and these are displacement reactions and highly exothermic reactions. Now this reaction which you saw here, okay, this is also called as thermite reaction. Okay, it is a very very important question. It is also called as thermite reaction. Very very important question. Why do we call this reaction as thermite reaction? Because actually, what is the commercial use, or how do we where do we use this reaction? I will tell you. You have this railway tracks, no? Okay, due to the you call it due to the friction or force, or due to different weather conditions, or due to the mechanical action, because trains keep moving on the railway tracks. These railway tracks will get cracks in between. Okay, these tracks will get cracks in between. Now, to fix, okay, we have to fix these cracks. Okay, we have to fix these cracks in the okay, we have to fix these cracks in the railway tracks. So what do we do to fix these cracks in the railway tracks? Okay, what do we do? How can we fix the cracks in the railway tracks? We use this thermite reaction to fix the cracks in the railway tracks. Now, where you see now, for example, imagine this is my crack. Okay, in the railway track. Now, in this reaction, you get iron in the form in molten form. In this reaction, you get iron in the molten form. So we pour that iron into this crack. Okay, we pour we pour this molten hot iron into this broken, broken or cracked railway track. Clear? Now this crack gets filled, and as soon as it's as soon as as soon as it cools down into the crack, everything gets sorted. Okay, everything gets sorted. Clear? Okay, and the crack also gets fixed. When it was in the molten form, you have poured it into the crack, and it cools down and it fixes the crack in the railway track. That is the reason it is very much used in fixing the cracks in the railway tracks. And what do you call this reaction as? I call this reaction as thermite reaction. So please remember, no I aluminium sorry manganese and iron oxides are reduced using aluminum, which is a highly reactive metal, very highly exothermic reaction. And it also has a commercial use, which is your thermite reaction, which is used to fix the cracks in the railway tracks. Okay, let us see the B bit in this question. Why can metals high up in the reactivity series cannot be obtained by reduction of the oxides by carbon? Okay, very important question. This question keeps coming always. Now I have the highly reactive elements here: potassium, sodium, okay, calcium, okay, magnesium, aluminium. Now these no these highly reactive elements, we usually what we do, they are high up in the reactivity series. They are not obtained by reduction of their oxides by carbon. Now if you take oxides of any of these elements, either you take K2O, or you take Na2O, or you take CaO, or you take magnesium oxide, or you take aluminum oxide. These are highly reactive metals. When we say them as highly reactive metals, it is very much obvious they easily react with oxygen and they exist in oxide form. Very much obvious that they react with oxygen and exist in oxide form, or in Earth's crust they are mostly available in the oxide form only. So mostly the highly reactive elements, they are obtained as oxides or chlorides. Highly reactive elements, they are mostly obtained as oxides and chlorides. Now he's asking, why don't we use carbon as a reducing agent here? Why don't we use carbon as a reducing agent here to convert them into their respective metals like potassium, sodium, calcium, magnesium, aluminum? Okay, we don't use them. We don't use carbon. The reason is, okay, now when carbon is trying to go and reduce these oxides, when carbon is going and trying to reduce these oxides, all the highly reactive elements, okay, all highly reactive elements have more affinity or love towards oxygen. Okay, all highly reactive elements, this statement please remember, all highly reactive elements, all highly reactive metals have, okay, all highly reactive, okay, all highly reactive elements, reactive metals have more affinity, more affinity towards oxygen. Okay, more affinity towards oxygen, more affinity towards oxygen than carbon. Okay, all highly reactive metals have more affinity towards oxygen than carbon. This statement is very important. Please remember. Now, all highly reactive metals, they have more love towards oxygen. They want to be bonded with oxygen. They have more love towards getting bonded with oxygen. Now, when carbon comes and tries to reduce them, if carbon is trying to reduce them, what should carbon do? Carbon should break this metal oxygen bond. okay, and and help in the process of reduction. But because these highly reactive metals have more affinity towards oxygen than carbon, when carbon comes to reduce them, they don't get reduced. That is the reason all highly reactive metals have more affinity towards oxygen than carbon. That is the reason we can't use them as reducing agents to reduce the highly reactive metal oxides into their respective metals. So highly reactive metal oxides cannot be displaced, cannot be reduced into their respective metals using carbon, because these highly reactive metals have more affinity towards oxygen than carbon. Okay, hope you understood this. Next question, with the help of an activity, explain the conditions under which the iron articles get rusted. Okay, now you have an activity in NCRT for this. You have an activity in NCRT for this. I'll try to explain you this using that activity. Okay, you have the activity. He's asking, explain the conditions under which iron articles get rusted. Okay, what are the conditions which are needed for the iron articles to get rusted? Further, there is an NCRT activity. Let us try to understand. Okay, let us try to understand this using this activity. Okay, let us try to understand this activity. Okay, now this is the activity given in NCRT. Okay, activity 3.14. Okay, activity 3.14. Now if you see here, you have taken three test tubes here. Okay, I have put the diagram in front of you so that you have a better understanding. Okay, you have three test tubes A, B, C in front of you. Okay, in both A, B, C, A, B and C, what do I have? I have three iron nails. Okay, in three of them, in three test tubes, I have three iron nails. Now, if you see the test tube one, okay, if you see the test tube one, what is the condition in the test tube one? Iron nails are there, so iron is there. What is the other condition I have? I have water in test tube A because iron nails are dipped in the water. I also have air in. Okay, I also have air in the test tube A. If you go to the test tube B, what are the conditions you see? I have my iron. Okay, because they are dipped in water, it is in contact with water. Now, do you see the presence of presence or the interaction of iron nails with air? No, I don't see any interaction of iron nails with air here, because there is a layer of oil that is preventing air to dissolve in the water. Okay, now when you have oil layer above the water, now the air will not come in contact with the iron nails. Air will not come in the contact with iron nails. Now here iron is only in contact with water. Now when you see the test tube, see here I have my iron nails. Okay, I didn't take any water, so there is no water in the test tube. And what else I have? I have anhydrous calcium chloride. Now what is the role of anhydrous calcium chloride? Anhydrous calcium chloride will take all the moisture from the air. Usually whenever you take air around you, it has moisture in it. If I take air around me right now, it has moisture in it. Now what am I doing? I am using anhydrous calcium chloride, which is used as a drying agent. It takes all the moisture from the test tube, so I call it as drying agent. So do I have presence of water here? No. Do I have presence of air or oxygen here? No, it is, there is no moisture. There is no, okay, there is no air. Sorry, there is air. Sorry, my bad. There is air. Okay, I didn't create any condition, vacuum condition, that there is no air. So I have air here. What did my anhydrous calcium chloride do here? It has removed all the moisture from the water. See, water as such is not there in the test tube. It is agreed. You people can say, ma'am, water is not there only. No, what is the point of putting anhydrous calcium chloride? Okay, I didn't take water, very good. But in air, you have moisture in it. Okay, in air, you have moisture in it. That is the reason. What is the thing is, to remove the moisture, what do we do here? To remove the moisture, we put what here? To remove the moisture, we put anhydrous calcium chloride. Okay, to remove the moisture, we put anhydrous calcium chloride. Now, if you see this, okay, yeah. Where do you see the rusting of iron nails here? You see rusting of iron nails in the test tube A. Okay, you see rusting of iron nails in the test tube A. In test tube, okay, in test tube B, you see there is no rusting. In test tube C also you see no rusting is taking place. Clear? In test tube C also I see no rusting in taking place. So by using this activity, or by looking at this activity, what do you conclude? What are the two necessary conditions I need for rusting? What are the two necessary conditions I need for rusting? For rusting, I need the presence of air, or especially I need the presence of oxygen which is present in the air, because oxygen is the most reactive component in the air. So what are the two necessary conditions for rusting? What are the two necessary conditions for rusting I need here? One is the presence of air or oxygen. One is presence of air or oxygen here. What is the other condition I need? Okay, I need other condition I need is the presence of water. So these are the two conditions needed for the rusting of iron, which is concluded using this activity. Okay, which is concluded using this activity. Hope you understood. We'll once go back to the question once. Yes. Okay, with the help of an activity, we have explained what are the conditions we need for the iron articles to get rusted. Okay, so this is now we are done with this question. All the three parts of the question we are done. Now let us see the questions. Okay, next question. Let us see the next question. Now when we go to the next question, what is given here? Name two metals which react violently with cold water. List any three observations which a student makes when these metals are dropped in a beaker containing water. Okay, now what are the two metals that can react violently with cold water? You people know this. Okay, what are the two metals we usually study which react violently with cold water? Sodium and potassium. Sodium and potassium are highly reactive metals. Sodium and potassium are highly reactive metals. That is the reason they react violently with the cold water. Okay, they are highly reactive metals. So they react violently with cold water. They react violently with cold water. Let us quickly see how they react violently with cold water. Now I have a beaker which is in which water is there. Now whenever I put sodium or potassium into it, okay, whenever I put sodium or potassium into it, because sodium or potassium, they have less density. As soon as you put into the water, they float onto the surface. Okay, they float onto the surface. Now when they float onto the surface, it is in contact with water. So what reaction can happen here? Okay, potassium plus water gives potassium hydroxide plus hydrogen gas, and this reaction gives enormous amount of heat. Okay, and this reaction gives enormous amount of heat. Clear with this? Okay, this reaction gives enormous amount of heat. Now due to the enormous amount of heat, now you see in this reaction hydrogen gas is produced. Now due to the enormous amount of heat that is produced, these hydrogen violently reacts with the atmospheric oxygen. Okay, these hydrogen enormously react, okay, violently reacts with the atmospheric oxygen, and that will release lot of heat, and it will make this reaction a very violent reaction. Clear with this? Okay, so name two metals that react violently with cold water. Now my two metals are potassium and sodium. List any two observations which a student can make when these metals are dropped in a beaker containing water. I already told you what exactly is happening when the metal is dropped into the water. Okay, so what are the three observations you can see here? Okay, what are the three observations you see here? I can see that the metals float on water. Okay, I can say that metals float on water because they have low density. Metals float on water can be your one observation. What is the other observation I see? Okay, what is the other observation I see? I see release of hydrogen gas. Okay, I see the release of hydrogen gas, which can, okay, release of hydrogen gas. What else can I see here? I can also see hydrogen gas violently reacting with hydrogen gas with oxygen. How is this reaction? It is a very violent reaction. That is the reason I see what? Okay, I see what here? I see lot of heat getting produced here. And what is making hydrogen violently react with oxygen? The heat produced in this reaction. And no, what is the observation for me? Because of this heat helping hydrogen to no, explosively react with oxygen, this is a very violent reaction. So these are my three major observations. Okay, these are my three major observations. Metals float on water, release of hydrogen gas. Okay, and I also see using the heat produced in the reaction, hydrogen violently reacts with oxygen, making it a very explosive reaction. Okay, what do all these conditions make it? They make it a very explosive reaction. They make it a very explosive reaction. I hope this is clear. Make it a very explosive reaction. Okay, hope you got this. Okay, I have explained how is it happening. As soon as you put these metals in water, because they have less density, they float on water. Now the reaction happens, hydrogen gas is produced. Now due to the heat produced in the reaction, this hydrogen gas violently reacts with the atmospheric oxygen, making it a very violent explosive reaction. Clear? Write a test to identify the gas evolved during the reaction of these metals with water. What is the gas evolved for me? The gas evolved for me is my hydrogen gas. Now, how do you test the hydrogen gas? Test for hydrogen gas. Okay, test for hydrogen gas. How do we test hydrogen gas? Okay, okay, for example, in a test tube I'm performing performing certain reaction. In this reaction, what happened? Hydrogen gas got evolved. In this reaction, hydrogen gas got evolved. How can I test this gas? I will take a burning splinter. Okay, I will take a burning splinter. Okay, I will take a burning splinter, and I'll place the burning splinter near the mouth of the test tube. I'll take a burning splinter. Okay, and I'll bring the burning splinter at the mouth of the test tube, because hydrogen gas is released. If hydrogen gas is released in this reaction, okay, then what will happen? Okay, whatever burning splinter it is there, it blows off with a pop sound. What happens to the burning splinter? It blows off with a pop sound. It blows off with a pop sound. So how do you identify? You get a no, you get a very typical kind of pop sound. So what happens when I bring the burning splinter near the mouth of a test tube, which is in which hydrogen gas is released, the burning splinter blows off with a pop sound. Clear with this? It blows off with a pop sound. Now this we call the no, this test also called as pop squeaky test, or we call it as, burning splinter test. Now whatever you call it as, but basically what happens whenever the hydrogen gas is released and you're bringing a burning splinter near the mouth of the test tube, the burning splinter blows off with a pop sound, and we also call this as the pop test. Okay, these are the two theory questions that came in the year 2025 for the board exams. Hope you understood. I tried to explain in the best way possible. Hope you loved it. In the next no, session, I'll see you with more PYQs from the year 2025 for the other chapter, acids, bases, and salts. Till then, this is Kirti ma'am signing off.